Hello and welcome to our final project for feedback control systems. I'm Christopher Lignon.
I'm Reichi Sun.
I'm Joel Mendoza, and we will be doing our project on the UAV problem.
In the modern era, companies like Amazon send 500 million plus packages through our delivery system. To solve this large influx, we are employing the use of UAVs. It is supposed to be more time and cost efficient. However, UAVs are still in early implementation stages. There's a social stigma that there is a large displacement in height when flying UAVs, which causes a bunch of crashes. So our task for our project is to be able to control the height of a UAV. Based on our previous slide and research, we have determined that settling time, overshoot, and steady state error are the three main components affecting our system. Settling time is how quickly the UAV stabilizes in air. Overshoot is how large our displacement is compared to our stabilization point. And steady state error is what we'd like to minimize for user input error. Our controller type we chose is PD controller. This is the block diagram here, which will be used to create our initial design of our control system.
To model our system, we came up with this free body diagram and this block diagram. The mass in the free body diagram represents the UAV with the rotor force pointed up and the gravitational force pointed down. The damper included represents air resistance. According to our research, we found that the mass is 10 kilograms about, and the damping ratio to be about 0.5. And the block diagram has an input of the gravitational force and the rotor force, while the output is the height of the system. Using the transfer function we obtained earlier, we found the root locus plot for the transfer function. And as you can see, that there is one pole at the origin at s equals 0, which makes the transfer function unstable. And we further proved this by analyzing the Routh-Hurwitz. You can see that the first column has a 0 in it, which means that it's spiral unstable.
In order to implement a proper design, we first looked at the step response of the closed loop system without a controller. So as you can see from the step response, the settling time is extremely large, it's just over 200 seconds. The system also has very high oscillations, which would not be viable for a UAV. We would want to reduce the settling time and we would want to reduce overshoot for this situation. So we ended up deciding to use a PD control. Our specifications would be settling time to be less than 4.6 seconds, overshoot to be less than 5%, and make sure to have a steady state error of less than or equal to 0. After designating our PD controller, we were able to find our controller transfer function to be Kp plus Kds. We can then use this controller and implement it into our system block diagram as we have our controller and our original plan, which is just our original transfer function. We can then close loop the system and find the closed loop system transfer function, which we relate the output height over the input force. We find that to be Kds plus Kp over ms squared plus b plus Kd times s plus Kp, which as you can see is a second order system based off of the 2 in front of the s. We can then use this and previous specs such as %OS to be less than 5% to find zeta equal to 0.7, which we can relate with the OS versus zeta graph. We can then use the fact that our system is second order and solve for Kp and Kd gains. Using the t settling to be less than 4.6 seconds and the newfound zeta to be 0.7, we can calculate omega n. We calculated omega n to be 1.44. We can then solve for Kp, as Kp is just omega n squared, which we found to be Kp is greater than or equal to 2.10. After calculating Kp, we can then derive Kd, relating that to b plus Kd is equal to 2 zeta omega n. After that, we solved Kd to be greater than or equal to 1.5. We can then take those gains, plug it back into the equation, and find the zeta that we found there. In order to further implement our system, we decided to make sure that our controller would create a stable system. We took a simple Routh-Hurwitz test in which we took the denominator of our controller closed loop transfer function and we used Routh-Hurwitz in order to prove the system would be biostable. As you can see, the left half column of this array is positive, therefore proving the system is stable. We then went on to prove steady state error and to show that steady state error would be 0. Since it is a type 1 system, as the original transfer function has an integrator, it will always equal 0. But in order to prove the derivation, we took the open loop system of our controller block diagram in which we implemented it into the derivation of a type 1 system. We then used the final value theorem in order to prove that steady state error would equal 0. After verifying our system, we found that we were successful as all specifications were met. Our original overshoot was supposed to be less than 5%, which can be seen as met since our overshoot was calculated to be 3.18 based off of the step response graph, as well as our settling time was supposed to be less than 4.6 seconds, and we met that as if it was 1.49 seconds, which can be seen here as well from this step response. Our steady state error was proved to be 0 using the final value theorem. Using this root locus closed loop system, we also saw that our system was stable as the only pole lied within the region that it was supposed to lie within. Our gain values were calculated to be 64.267 for Kp and 121.19 for Kd, which were greater than the values stated previously, therefore those were also valid. After iterating the model in Simulink, we realized that the step response matched, proving our results even more valid. As you can see, the step response from Simulink matched the step response as if when we ran it in command lines within MATLAB. We plugged in our Kp, Kd values, and then we took a step response of that, and they matched. The peak amplitude were both 1.03, the overshoot was 3.18, which was exact same, and the settling time was also 1.49, proving our specifications. In order to further analyze our system, we looked at the robustness of the system. We tried to find gain margin and phase margin. Gain margin is calculated where it crosses negative 180 in the phase diagram. Since it never crossed, it's infinity. Phase margin is calculated when it crosses 0 dB, which can be seen here at about 12.1 radians per second, which is also a crossover frequency. That difference is then found to be 87.7 degrees. Using phase margin and crossover frequency, we can then calculate time delay, which is 0.125 seconds. We then plug that into Simulink to prove our system stable, and it was stable.
In conclusion, our system successfully regulated the height of the UAV with desired specs through the use of PD control. All specifications were met. We have a really low settling time, virtually no overshoot, and a steady state error of 0. Our control system is also stable, which makes it a great tool to increase the